And let me tell you one very interesting fact that you know what? The sun is actually a black body. Yes. A lot of people have a misconception and they think that a black body should look black, but there is nothing like that. A black body may look yellow, may look green, may look blue, depends. And what does it depend on? We're going to see that, and we are also going to start solving a very interesting problem on sun's radiation energy which is received on Earth. In fact, that was a question which was previously asked in JEE. With me, Shreyas, your master teacher for physics at Vedantu. Hello everyone, how all the new minions? Please introduce yourself to each other, make sure you make friends. And by the way, this is Shreyas here, and I teach physics not just on YouTube but also on the regular platform on the app of Vedantu. So I have been teaching for quite some time now, and with my experience I bring in a lot of interesting stuff like the innovative methods that I take up, and also all the interesting problems that I have planned for all of you, and a lot of tips, strategy sessions for the upcoming JEE Mains as well as advanced, as well as bits, as well as for the next year preparation as well. So welcome Anke, Dhanush, Yalini, VK, Pankaj, Uncharted, Kirito, Marvin, welcome. Yes. Oh Pankaj, please make sure that you do not put one word as a separate chat. Make sure that you do not spam out there. All right. Hello Kiran, hello Nitish, welcome Priyanka. Yes, let's begin with today's session, and before that let me also tell you can follow me on Instagram. That's my handle, Shreyas_Vedantu, where I'll keep posting regularly on the latest updates, news, videos, interesting facts, motivational tips and stuff like that. And all the new timers out here, do not forget to hit the subscribe button, because only when you subscribe you'll get all the latest information from this channel. And this is a very special channel because this is in English, and this is meant for all the English medium students who are preparing for the JEE examination. And also do not forget to hit the like button out there, because you have to show your support to all of us by smashing that like button out there. All right. So Uncharted, if there is a Menti coming up, definitely will tell you. But for this week, this is what we have planned. So thermal physics Monday, Tuesday, and on Friday, there is a marathon session, a big session, where we are going to talk about first law, all the different processes and different previous year questions on thermodynamics and other chapters. Also on Thursday, we have a very special session, the most important and expected topics in the upcoming examination. And EMI, the last part, AC and LCR circuits, will be covered tomorrow at 7 o'clock. And Saturday, we are going to have a mock test discussion. I'm going to give you a test and you're going to solve that question paper beforehand only, and we're going to discuss all those questions. All of this every day at 7 o'clock. Keep this in mind. You can take a screenshot. Also, it's going to be there in the description box. Yes, Ankit, I'll definitely reply to your comments. I couldn't really find time for replying every comment out there yesterday, but for sure, I'll definitely try and make it a point that I reply by tomorrow at least. Yes, let's begin with the session, and let's start with some examples of radiation. Now, yesterday I told you that radiation is a type or a method of transfer of energy from one body to the other body where medium is not necessary. Even when there is medium, yes, radiation can occur, but even when the medium is not there, radiation can occur from one body to the other body. Now, the thing is, radiation is really quick, and radiation is nothing but electromagnetic waves. So some examples will be you taking the warmth from a bonfire or from a fire which is just lit in the forest or something like that, and the heat is felt not because of the particles of the air or the wind blowing, but just because this fire is emitting electromagnetic waves in all the directions, and a part of those electromagnetic waves fall on your hand or your body. Another example is obviously the heat received from the sun to the earth. There is nothing between the sun and the earth. there is vacuum, yet that energy from the sun is received on the earth, and that is through electromagnetic waves. Remember, light is a small part which is a visible part of the electromagnetic waves, but there are different kinds of electromagnetic waves like normal light, infrared, ultraviolet, microwave, long radio waves, alpha, gamma rays and stuff like that. So another one is X-rays. So X-ray is nothing but radiation, of course. I hope you guys are understanding this, and the microwave that you would have definitely used in your kitchen. So all these are really good examples of radiation. So radiation is at the end of the day nothing but electromagnetic waves. Keep this in mind. So it will follow all the principles of light or in general electromagnetic waves, like the energy of a photon is hf, it can undergo reflection, it can undergo refraction, and all those things like speed of light is frequency into wavelength and stuff like that. So those things are common for all electromagnetic waves. There is nothing extraordinary about it. Now let's see, what does exactly radiation depend on? Now radiation depends on three things, and let's remember this because that is very important for solving problems. Number one, what is that number one thing? The amount of radiation depends on, understand the area of the surface. How big is that area? Even right now, I am radiating energy. Yes, I am radiating light. Even this pen, even the book in front of you, even the table on which probably you have kept your books, or the floor or the walls, everything radiates energy as long as the temperature is more than 0 Kelvin. And that amount of energy radiated depends on the surface area. Keep this in mind. More the area, more the amount of radiation. Number two, it depends on the surface. Like I was saying, anything above 0 Kelvin radiates energy. Now more the temperature, more the energy which will be radiated. But remember, at 0 Kelvin, hypothetically, if some object goes, then the amount of energy radiated will be 0. Yes. So when does radiation become dangerous? Radiation becomes dangerous only when the frequencies are in that dangerous zone, like X-rays or gamma rays and stuff like that. So otherwise, if normal radiation like red light or blue light falls on me, it's not at all harmful. But if UV radiation falls on me, then they are highly energetic, and that certain frequencies are dangerous to the skin or tissues of the human body. I hope this is clear. So basically, understand, everything around you will be radiating energy because the molecules are continuously moving, and anything above 0 Kelvin will have molecules which are vibrating, translating, etc., and they will radiate out energy, and that depends on three things. First two are area of the surface. Remember, radiation is a surface phenomena. Everything, even sun is radiating energy. The amount of energy which is given out by the sun depends on the surface area of the sun. Number two, temperature of the surface. So the energy radiated by the sun depends on the surface temperature of the sun, not what is there inside. Keep this in mind. And lastly, it depends on the nature of the surface. That means if I have a steel ball and if I have, let's say, a ball made of stone, okay, both of them might have the same temperature, same area, but they will not emit the same radiation. Yes, that's very important. It depends on the nature of the surface. Certain surfaces emit more radiation and certain surfaces emit less radiation. That surface which emits the most radiation is called as the black body. Keep this in mind. The surface for a given area and for a given temperature which emits the most radiation is called as a black body. I hope this is clear. Alright, so let's see the formula for that. So that is given by Stefan and Boltzmann. The amount of radiation emitted by any body is given by, okay, any body like this pen, your book, your hand, your face, the wall, the floor, anything. That energy which is emitted is given by dq by dt, but I'll put a symbol like E over here. This E stands for emitted heat per unit time. So generally it is written down as Q dot. This dot stands for the derivative, differentiation with respect to time, is equal to, remember this, three factors should come. One is, area, second is temperature, and third is nature. So this is how it looks like. E sigma A, temperature raised to 4. This is this formula which you must remember. Now, what are all these terms? Let me tell you that first. This is expressed in watts because this is joules per second, the amount of energy which is going to be emitted per unit time. So that is joules per second or watts. What is this E? I will talk about it in the next slide, but for now, understand it is nothing but called as emissivity. It is just called as emissivity. And for a black body, I'll tell you, E is 1. For other bodies, E is less than 1. We'll talk about it in the next slide. For now, just understand it is called as emissivity. This one is called as your Stefan-Boltzmann constant, and that value is very easy to remember. Just remember the numbers 5, 6, 7 and 8, and just put a minus sign here and just put a dot here. 5.67 into 10 to the power minus 8. That's the value of Stefan-Boltzmann constant. Keep this in mind. This is obviously the area of the surface, and this is obviously the temperature, be careful, in Kelvin, of the surface. Everything is of the surface. I hope this is clear now. Everybody understanding this? I'm very good, Surur. Thank you very much. Yes. So this is the formula which you should remember. Very good, we can noting it down. Does black body absorb radiation? Yes, it does. Yes, Kirito, black hole is also considered like a black body. There is a different theory for that, which Stephen Hawking gave. We can probably talk about it someday, some other day. But yes, that's also an interesting thing to note. Yes. Now, yes, Ankit, that's a very interesting suggestion. Definitely, I'll consider it. Now, if everybody has understood this, yes, temperature is always in Kelvin. Yes, correct. Yes. Cool. Now, the next important thing, like I was telling you, we'll talk about black body and emissivity. Now, what is a black body? Now, black body may not necessarily look black. Please understand that. Black body by definition is something which absorbs the most and it also emits the most. Yes, both ways. Black body is something which absorbs the most and which can emit the most out of all the bodies which you can compare at the same temperature of the same area. So, if for example, QE is the amount of energy emitted by some random body. This is the amount of energy emitted by, let's say, ceramic or stone or plastic or human, doesn't matter. If I divide this with the amount of energy which will be emitted by a specific or basically black body, then understand this value is always going to be less than this value. This is the highest. This is always the highest number. This is always going to be less than the corresponding black body. Then that ratio is called as emissivity, and this is what you should remember. Okay, this is called as emissivity. So emissivity, E, small e, is amount of energy emitted by a normal body upon amount of energy radiated by a black body. That is why I said E is always less than 1, because no such body, alright, will have perfectly 1, but it can be very, very close to 1. So that will be a very ideal scenario of a black body. I hope this is clear. I hope this is clear. Yes, Surur, we are going to come to something called as Kirchhoff's law, where we'll be talking about good emitters and good absorbers very soon. Alright, so remember this. Okay, now you can make a very good black body by a very simple arrangement. All you need is let's say a spherical object and a small hole, and coat the inner surface of that spherical body. It's a hollow object. Coat it with a black paint. Okay, coat it with a black paint. Now imagine some light enters inside it. Imagine some light enters inside it. Let's say 99% gets absorbed. What will happen then? Only 1% is remaining. That will get reflected. At the next reflection, 99% of that remaining 1% will get absorbed. So only 1% of that remaining part will get reflected. So that will be very faint. And in the next reflection, 99% of that remaining will get absorbed. Hardly anything will be remaining. I think after some 6-7 reflections, hardly any light will be left. So won't this object act like almost like an ideal black body? So the paint which you used to color it from the inner side was not an ideal black body, but you made this body as a whole behave like an ideal black body because of these multiple reflections out here. So this is a very good example of how you can make a very good black body at home itself. I hope this is clear. Yes, yes. So different materials can be used. All right, so it's not necessary you have to use a specific material. You can use whichever material which has good absorbing capabilities on the inner side. Lamp black is one such material. Okay, I hope this is very clear. Now let's solve a question. Okay, cool. Let's solve the question. Well, somebody is saying, can I use it as a battery? Oh yes, if you have thermal batteries, then why not? Is it a revision section, Devdatta? Actually, it can be used for revision as well as for all those people who have some basic idea of radiation, who have studied radiation in school but maybe had some doubts, and maybe you have learned this in coaching but you did not fully understand it. So it's all basically, more like revision plus studies. So I will teach you theory over here. I'll give you the most important points and you'll be solving problems. Don't worry, Ankit, like I said, I'll be replying to all your comments later on. Yes, in winter you should wear black. Correct, because think about it, it will absorb a lot of energy. Yes, and it will keep you a little bit warm. Okay, so pinhole is made in a hollow sphere of radius 5 centimeters whose inner wall is 727 degrees Celsius. Find the power radiated per unit area, and they have given you the Stephen's constant, and they have also given you the emissivity. So let's try and solve this particular question. So come on guys, think about it. How are you going to proceed with this? So first of all, try and understand all that energy is going to come, okay, from a small hole of radius 5 centimeters. So there is a small hole in a big sphere, okay, and that radius is basically 5 centimeters, and there is some energy which is going to be radiated from this point or from this surface. So think about it, the amount of energy radiated, okay, or emitted is equal to E sigma A T raised to 4. What is E? 0.2. What is sigma? They have given it to be 5.7 into 10 to the power minus 8, okay, multiplied by okay, area will be pi r square because it's a circle. So pi is 22 by 7 multiplied by radius is 0.05, okay, whole square, okay, this is the area, into temperature. Okay, this is 727 degrees Celsius converted into Kelvin, which is 1000 Kelvin, guys. So it will be 1000 raised to 4. Now do the math and you will get the answer. That's it. So that's how you need to solve this problem. Now you solve this, I believe the answer that you should get is very close to 89.4 or 5 approximately watts. So that's what you will get the answer as if you solve this. All right, but I hope you understood this basic problem. Let's see. Yes, 89.5 watts. So yes, Devta, it will be useful for February attempt. Every attempt will have full syllabus, right? Yes. So obviously it will be useful for all the attempts, in fact. Okay, now let's go to the next question. Very interesting question. It was asked in previous years. Very important question. But before that, let me also tell you, for all the new students out here who have probably missed that opportunity, but still the window is open for joining the crash course. The crash course is like a complete batch which covers all the syllabus of 11th and 12th. Like you can see, this is the schedule for the 11th and 12th syllabus which will be covered in this crash course. All the topics will be covered in these sessions, and then also the maths and the chemistry syllabus, all physical, organic, inorganic, starting from 28 Jan to 10th March. I know you have missed a few lectures. but you can always watch the replay any number of times. Even in the future, let's say for example, on 10th February, you did not understand, for example, GOC. You can again watch that lecture 100 times till you understand it if you want to. And yeah, this is the maths syllabus which will be covered. In fact, it's the entire syllabus. And guys, like I was telling, even if you have some doubt, let's say you did not understand probability, or maybe you have some problems which you could not solve in probability, then you can ask our doubt experts. Yes, that's what we give you, all our doubt experts who will be solving all your doubts from morning till night, and they are dedicated doubt experts, all right, so that they can solve all your doubts, unlimited doubts, either from NCERT or from previous years or from any other book that you have, so that there is no confusion, number one. Number two, you know for sure this is the answer. Number three, you get all the answers really quick, so you don't have to waste time doing research or getting wrong answers from your friends. That's why we give you this, as well as, like I just said, rapid revision and full syllabus coverage right from scratch. Also, whatever the teacher is going to write on the board, everything will be available in the form of notes, plus extra assignments, and all the modules whatever are required for the revision will be handed over to you. Keep this in mind. And this is the best part, guys. Come on, mock test. Yes, 20 mock tests for all of you with discussion sessions. That's very important. Discussion, if it doesn't happen, then there is no point. And lastly, obviously, you get all the important tips and strategy before the examination by our master teachers, Anand Sir, Pulkit Sir, and many other teachers out here. So all of this combined package is available till your last attempt. Understand, you can utilize fully these doubts. Even if the crash course will get over in a month, this doubt solving will be available till the last attempt. Keep this in mind. It's not like if the crash course ends on 5th March or 10th March, that's it. No, it's available till the end. That's the best part about it. So I feel you should make full use of it, because in the last few days you need that extra push. You need somebody to guide you and support you. So this will be a very good organized way of making sure you practice things regularly, and obviously you whatever misconceptions you have are getting cleared. So all of this at 10,000, but you know the discount coupon is out here, SHCC. Using that, you get 2,000 rupees off, that is 20% off, and that's the final price, 8,000 rupees. That's a good deal. I feel you should consider it. Check the link below. There will be a link in the description box. Open it up, check all the details, enroll, and make sure you use the coupon code SHCC so that you can avail 20% off. That's very, very important. Yes. So let's get going. Somebody was asking, why is it pi r square? Because there was a hole opening of pi r square, or sorry, of radius r. From that radius, understand, you know, the radiation is coming, and the radiation was in fact coming from the inner walls. In fact, if you look at the previous question, okay, 1 second. Yeah, if you look at the previous question, it said, you know, the inner wall temperature is 727. So that's why it's not the surface area of the sphere, and a lot of people do a mistake. They write it as 4 pi r square and then they get a wrong answer. So be careful about it. It was the inner wall, and from that inner wall it is coming through a small area of radius 5 centimeters. So that's how you get it. I hope it is clear. Yes, when you use 4 pi r square, you will not get the answer. Correct. A lot of people think it's from the outside. No, it's from the inside. Correct. Cool. So I'm guessing I have answered all your doubts out here. Okay, very good. Yes, calculation is boring. Yes. So Vignesh, I guess I have answered your doubt. So it comes at a small cost, Vignesh, and I feel that cost is justified because you know you have to pay the teachers who are teaching you and stuff like that. So that small cost takes into account all the people who will be supporting you, your class teachers, those doubt experts. Understand, you need to pay those salaries, right? So that's why that small cost, we have kept it very low of just 8,000 rupees. Okay. In the previous question, if it is per unit area, yes, uncharted, then you should divide it with the total surface area. Correct. Now, this is a very good question, 2016 question. Assuming that the sun is a spherical body of radius r at a temperature of T Kelvin, Evaluate the total radiant power incident on the earth at a distance small r from the sun, where r0 is the radius of the earth and sigma is Stefan's constant. Okay, let's try and do this. Now, a lot of people will make a lot of mistakes here. So let's see how do we solve this question. First of all, let's see what and all is given. This is given to be capital R, and the temperature of the sun is T, and it is obviously radiating energy in all the directions like this. Okay, so it is radiating energy in all the directions. Now, not all the energy will be received by the sun, not by the earth. The distance between earth and the sun is given to be small r. Okay, this is the distance between the sun and the earth. Observe that. Look at the variables very carefully. There are 3 different r's. Next, this is the earth. Okay, if this is the earth, think of it this way. The total amount of energy which will be falling on the earth, think of it like this. If this is a sphere, okay, the amount of energy which will fall on the earth will be same as that on a spherical disk or just a disk whose radius is the radius of the earth. I'll repeat myself again. This is very interesting. If this is the earth, solid sphere, the amount of energy, some amount of energy will be falling on the earth. Okay, on the earth will be same as a disk of the same radius as that of the earth, and which is kept in the path of light. I hope this is clear. Very, very interesting. Very, very interesting. See, if it is clear, this concept is very important, because those of you who will understand this particular concept can only solve the problem, and that is why it is a previous year question. Now, if you have understood this, so all that I need over here is only that circular area of that disk. So think of this like a disk, and that disk has a radius of r0, which is the radius of the earth. That's all you need. Now, how much actual energy falls on the earth out of the total energy which is radiated from the sun? Let's do one thing. Let's figure out from the sun, if you are at a distance of r, what is the intensity of light? Yes, power per unit area. So what is that power per unit area at a distance of small r from the sun? That will be equal to, think about it, whatever energy is coming out of the sun, it will go in all the directions. And imagine a big hollow sphere. Imagine a big hollow sphere of radius small r. Imagine a big hollow sphere of radius small r, and all that energy will fall on that hollow sphere of radius r. So what is the energy which is falling per unit time, per unit area on that big hollow sphere? That will be that energy which will be coming out. What is that energy which is coming out? E sigma area of the sun, okay, into temperature of the sun, all right, whole raised to 4, okay, divided by the total area. Just visualize the total area of that imaginary sphere that you can visualize. What will be that area? It will be 4 pi small r square. This is very important. See if you are able to understand it. This r0 is very small, guys. This is negligible, okay, and this r is also negligible as compared to the distance between the sun and the earth. So you can neglect that r and small r0. So think of a point object. It is emitting radiation in all the directions. On that imaginary sphere of radius small r, the energy per unit area will be the total energy upon that area of the sphere. That's how it is. Now, if this is clear, what is that area of the sun? Let's write it down. Well, E sigma area of the sun is going to be 4 pi the radius of the sun square. Temperature of the sun is T raised to 4 by 4 pi small r square. Now we know what is going to happen. Obviously that 4 pi and 4 pi is going to get cancelled. Okay, then the next thing that I'm going to do, what is the energy incident? Okay, what is the energy incident on the earth? What is the energy incident on the earth? That energy will be this intensity. Remember, this intensity will be in watts per meter square multiplied by the area of that disk, which is in meter square. So watts per meter square, this was energy per meter square, into the area of this disk will give me how much energy is falling per unit time. So that is going to be equal to E sigma r square t raised to 4 divided by small r square into pi. Radius of the disk is r naught square. If you want, rearrange it, and if we are assuming the sun to be a black body, then E will be 1. So if sun is a black body, then E will be 1, otherwise E will stay. So it will be E sigma r square t raised to 4 pi r naught square by small r square. That should be the final answer. I hope this is clear. No. Why are we taking 4 pi r square over here? Because think about it, that energy which comes from the sun will go in all the directions, left, right, up, down, back, forward, everywhere. So that imaginary sphere has a surface area of 4 pi r square. That is why. Okay, I hope this is clear. No problem, Diya, you can just rewind back a little bit. Narinder, good evening. Daniel, no problem. Just please go behind and just catch up if you are a little bit late. No problem. Yes, I hope this is clear and this is understood. If it is a black body, then take this as a 1 value. Okay, so keep this as 1. Okay, cool. So let's get going. Yes, this is the answer. So I think they have considered the sun to be a black body, so E will be 1, and this is the answer. Cool. So let's get going to the next question, and for that we need to, so we are considering the energy received by the disk. Yes, correct. So that's why in the end, Kirito, what I did was, so the energy received by the disk will be that intensity of light. So intensity of light multiplied by pi, the radius of that. So it will be r naught square. So that's why finally I multiplied by pi r naught square. I hope this is clear. In that previous question, that pinhole was different. That pinhole was somewhere here. So all that energy which came from inside, all right, has eventually come out from here. So eventually it comes out from here. So that's why only this area was considered. I hope that makes sense. Okay, cool. Let's get going. Ankit, not needed for understanding ultraviolet catastrophe and all that. Don't worry, don't break your head on all those things. Okay, next up. Okay, next up is Wien's displacement law. See guys, what I was telling you some time back. Understand that a black body need not look black. It can look orange, it can look yellow, it can look green. Everything in this universe above 0 Kelvin emits radiation. Okay, so if you take a body and if you see that it has some temperature, it is emitting radiation. But the problem is that radiation may or may not lie in the visible spectrum. Certain temperatures, it emits radiation which lies in the visible spectrum. Now it so happens that the sun's temperature is such that the wavelengths which are emitted lie in the visible spectrum, because of which you can see the sun. But there could be other stars, or maybe there could be some object which is hot, which is emitting radiation, but you cannot see it. Why? Because it is outside your visible range. Maybe it is ultraviolet, maybe it's infrared, maybe it's X-rays, maybe it's gamma rays, doesn't matter. But it's outside your visible range. So understand, the radiation which is emitted depends on the temperature as well. The wavelength also depends on the temperature. So you might be thinking, do we humans also emit radiation? Yes. So you'll be wondering, sir, what color are we? You'll be like, oh sir, I know, we are brown or black or white or whatever. No, you're not brown, black or white. The radiation that you emit at room temperature, that's around 300 Kelvin, lies in the infrared region. Yes, infrared region. Even if you turn this room dark, your body will be emitting infrared region spectrum and radiation. And the only problem is you cannot see infrared, so you need thermal cameras which can capture infrared rays so that you can see that radiation. I hope this is clear. I hope this is clear. Yes, yes. So that is why military and other people use those thermal vision goggles which capture infrared so that you can see the enemy or the thief or whosoever it is. That's how it is. Now, what is the law which relates temperature and wavelength? Look at this graph. This tells you the intensity of light for different wavelengths. Now, it so happens at 3000 Kelvin, the graph is like this. The graph has a maximum value somewhere around 1000 nanometers. If you increase the temperature to 4000 Kelvin, that maximum wavelength which is emitted, all right, most of the wavelengths which are emitted are somewhere between 500 and 1000. And if you increase the temperature further to 5000 Kelvin, you can see it goes very close to 500 nanometer. So you can see the wavelengths, the colors which are emitted depends on the temperature. And that law is called as the Wien's displacement law. So lambda max. So what is lambda max? This is lambda max. Understand? This value is lambda max. And this could be the probably temperature into temperature. All right, into temperature is 2.98 into 10 to the power minus 3. And be careful, this is meter Kelvin. Okay, this lambda is in meters, temperature is in Kelvin, then this constant is 2.98. So more the temperature, less is the lambda. They are inversely related to each other. Keep this in mind. Yes, I hope this is clear. Yes, you are supposed to remember this graph, but don't remember the values. That is not needed. All you need to remember is that number one, as you increase the temperature, the graph shifts towards the left. Okay, that's one. Also, the area under the graph, all right, that area under the graph gives you the energy. That is why this graph has also gone up, because when you increase the temperature, the energy which will be radiated also increases. So that's why the height of the graph has also increased for the same object. All right, so keep this in mind. Okay, let's solve this problem. Increasing the temperature of a black body, which one of these options do you think is correct? Come on, read all the options. Only one of them is correct. Think about it. Come on, come on, come on, come on, think. Yes. Come on, come on, come on, come on, think, think, think. Some of you are saying A, some of you are saying D. Prem says, hi Prem, join in. And if you are late, don't worry. You can always watch the replay and catch up. All right. Uncharted says D, Kirito says D. Okay, well, think about it. When you increase the temperature, according to Wien's displacement law, what will happen? Lambda max, that lambda which is emitted the most, will decrease. And frequency and wavelength are inversely related. Remember that. So hence the answer is D. Come on, think about it, guys. Because when temperature increases, lambda will decrease. And when lambda decreases, frequency will increase, because lambda into T is a constant and lambda into F is the speed of light. So that's how things work. So frequency will increase, wavelength will decrease for the maximum wavelengths or the radiation which will be emitted. I hope this is clear. Very good, very good. Let's get going to the next question. Here it is. Very interesting. A black body is at temperature of 5760 Kelvin, okay, and the energy of radiation emitted by the body at wavelength of 250 nanometer is U1, at 500 nanometer is U2, at 1000 nanometer is U3. Wien's constant is this. Which of the following is correct? Come on. The energy radiated by the body at wavelength this is so and so. Come on, think about it. What do you guys say? Come on, come on, come on, come on. Think about it. Come on, think about it. What do you guys think? This black body is emitting radiation. What do you guys think? should be the answer? Come on, come on, come on, come on. Very interesting question. It's not so simple, let me tell you that. Let me tell you that. They have given the Wien's constant to be some weird value. All right. They have given the Wien's constant to be some weird value. So keep that in mind. Think about it according to the question. According to the question. Think about it. Think about it. Think. Come on, guys. Yes, maybe D, maybe C. All right. Let's have a look then. Let's have a look. Now, what you need to do is this. I'll tell you what you need to do. See, guys, the graph for this, all right, maximum wavelength, all right, looks something like this. And we just figured out lambda max and temperature relationship. Lambda max into temperature is this value, 2.88. Not sure why they have given, oh, this is this is nm. Oh, that's fine. 2.88 into 10 to the power 6 nm. So this is okay, 10 to the power 6 nanometer Kelvin. That's fine. Okay. And now use this value of temperature. Use this value of temperature 5760. So lambda max will be equal to 2.88 into 10 to the power 6 divided by that temperature, which is 5760. So what is that value of lambda max that you're going to get? Come on, think about it. Yes, come on, think about it. What is the value of this that you're going to get? What is the value of this that you're going to get? Isn't it going to be 500 nanometers? Just check this out. Is it not going to be 500 nanometers? Now, here is the thing. 500 nanometers is this value. This is 500 nanometers. Okay. The energy radiated at 500 nanometers is U2. Okay. This is U2. Great. But the energy which will be radiated at 250 nanometers will be somewhere here. Isn't it? 250 nm will be somewhere here. And that is U1. Think about it. And at U3, the wavelength is 1000 nanometers. So this is 1000 nanometers and this will be U3. Now look at this graph and think for yourself which of these options are true. Obviously U1 is not 0. U3 is not 0. Is U1 more than U2 or U2 more than U1? Obviously U2 is more than U1. Think about it. Hence the correct answer should be D. I hope this is clear. I hope this is clear. Yes. Isn't it a brilliant question? I feel it's a brilliant question because you have to think for yourself which wavelength it will be maximum and accordingly compare the values. So that's why it is very important. Great. Let's get going to the next question. This is also a brilliant question. Two spherical stars, assume same size, all right, and same temperature, maybe not. Okay, only the areas are same. Okay, and the area under the spectral emissive power versus wavelength curve, that means that curve which we usually draw, the area under them is 16 times more than the other. So area for B is 16 times more than for A. What is the ratio of the maximum wavelengths which will be emitted for the respective radiation curves? Now let's see how do we solve this. Yes, crazy level of English out there. Now you should remember certain theory parts. That's why theory is also very important. A lot of people ignore that. First of all, what does the area under this graph give you? The area under this graph, okay, area under this particular graph gives you the amount of energy which is radiated. So this is the amount of energy which is radiated or emitted. Now think about it. Sphere B is having 16 times more area under the graph than of A. Okay, so basically QB is 16 times of QA. Now use Stephen's law. QB is nothing but E sigma A temperature of B raised to 4 is equal to 16 times E sigma A temperature of A raised to 4. Isn't that? Now think about it. E sigma A, both are getting cancelled. So if that's the scenario, if this is getting cancelled and this is getting cancelled, now take the fourth root of it. Now when you take the fourth root of it, it will be TB is equal to 2 into TA. That's it. TB is equal to 2 into TA. I hope this is clear. So now once I get this, I will write it like this. TB by TA will be 2:1. But remember, according to Wien's law, lambda into temperature is constant. Since lambda into temperature is a constant, think about it, lambda A by lambda B, shouldn't it be TB by TA? And what is TB by TA? 2:1. That should be the answer. So it sounds difficult, but it is not if you solve it like this. That's it. I hope this is clear. Okay? So very good question. You should be able to solve these kind of questions after attending these classes out here. All right, let's get going to the next question. 2:1. That's the answer. Now, let's go ahead, because I know a lot of students face problem in, radiation and conduction. I could have very well skipped all these theory classes and I could have just conducted problem sessions. And then, you will probably understand some problems, probably will not. But that is what, guys, I promised you. I will be telling you all the theory of all the chapters, and then simultaneously I will be doing problems. Also, once these theory sessions are over, within next few days, understand we will be doing only previous year questions, strategy sessions, tips and Menti quizzes and so many other things, mock tests and stuff like that. So you need to first of all understand these theories. All right, let's get going. Now, the radiation which falls on some body, meaning I am emitting some radiation, this pen is emitting some radiation, this radiation will fall on something else. That radiation which is incident can encounter three different things. One, a part of it can get reflected, a part of it may get absorbed within the body, and some part may also get transmitted to the other side. So, three things that can happen. The energy which is incident on a body can get reflected, can get absorbed, and the remaining will get transmitted. Now, if this is clear, think about it. If I tell you QI, okay, QI is the incident energy per unit time. That dot stands for rate of fall of energy, or rate at which the energy is incident. This will be equal to the energy which is reflected per unit time plus the energy which is absorbed per unit time, all right, plus the energy which is transmitted per unit time. Think about it. The energy which is incident will be equal to the energy which is reflected plus absorbed plus transmitted. This is one equation. Second equation, absorption coefficient is defined as how much energy gets absorbed upon how much is incident. For example, 100 joules per second is falling. Out of that, let's say 20 joules per second gets reflected. Rest, let's say 60, or let's say, I don't know, maybe 70 joules gets absorbed per second. Now 70 plus 20 is 90. Out of 100, 90 is getting reflected and absorbed. So remaining only 10 joules per second gets transmitted. So the absorption coefficient, think about it, the value of A in this case will be 70 by 100, that is 0.7. How much fraction gets absorbed? That is absorption coefficient. Next up, reflection coefficient. How much energy gets reflected upon how much energy was incident? So in this case, the reflection coefficient, you can see 20 is reflected out of 100, so it will be 0.2. And lastly, obviously you would have guessed, transmission coefficient is how much energy gets transmitted upon how much energy was incident. And in this case, you would have guessed it, the the transmission coefficient is 10 by 100, which is 0.1. Now it's not a surprise to see if you add these three numbers. All right, if you add these three numbers, you should always get it as 1, and that's the another important relationship which you should remember. Remember, 1 is equal to R plus A plus T. So lot of important formulas that you are learning right now. All right, so all the coefficients when added together will give you the value of 1. They should make up the total. All these fractions, when you add up, the total should be 1. Very good, very good. Yes, let's get going to the next set of problems. Are you guys ready? Wow, somebody is eating rats. Who is the Tom out here? Well, let's get going. Cool. I thought he was a fox. Now somebody has become a rat or a tomcat. All right, so let's get going. Yes, let's see some examples. Very interesting examples. Glass, perfect glass, an ideal glass should have T is equal to 1. Everything should transmit, but nothing is ideal in the world. Remember that. Okay, keep this in mind. Next, a perfect, very good mirror, best quality mirror should have reflection coefficient as 1. Yes, it should reflect everything, but there is no such mirror like that. Remember. And a perfect black body which should absorb everything. So A will be equal to 1. So you understand all these things. All right. I hope this is clear. Now, the most important law here is Kirchhoff's law, not Kirchhoff's voltage or current law. This is different. This Kirchhoff's law says good emitters are good absorbers and bad emitters are bad absorbers. Very simple to remember, and that tells you E is equal to A. Very important. Emissivity is equal to absorption coefficient. Remember, emissivity was the energy which is emitted, what is emitted by a normal body divided by, or what is emitted by a black body. That was the definition of emissivity. Absorption coefficient or absorptivity was nothing but how much energy is absorbed, all right, upon the total incident energy. That is how it was defined. These two are always equal. Keep this in mind. Cool. Oh, somebody is very hungry. Guys, please don't make me hungry. Yeah. What do you, I mean, like really, I've been like eating very less these days. Morning breakfast I skip. I just have juices and dry fruits in the morning. Afternoon, like a decent amount of lunch, and dinner there's hardly anything. Don't you think I'm becoming a little bit thinner, guys? I mean, if you have seen my past videos, do you feel that I have lost a little bit weight? Yes or no? Let me know. Yes, words of wisdom. People who teach a lot can also absorb a lot. People who do not help others also do not get anything in return. Yes. Due to 50 gulab jamun. Yes, Yalini, you caught me. Very good. Cool. Let's get going. Here is the next question. The object has transmission coefficient 0.1, reflection coefficient 0.2, and find the emissivity and the rate at which it will absorb 200 watts of total incident energy. No, Aishwar, I'm not exactly dieting, but I'm just having some healthy stuff these days. If I diet, I can't stay. I like eating. I'm a foodie. I love eating a lot of stuff. So whatever I eat in limited stuff, but I eat everything. That's how it is. Alright, thank you, Dinesh. Love you. Okay, chalo. So here it is. T is 1, R is 0.2. Remember, T plus R plus A is equal to 1. T is 0.1, R is 0.2, and A I do not know. So what is the value of A? It is 0.7. And remember, Kirchhoff's law said E is equal to A. Therefore, E is equal to 0.7. This is your first answer. Okay, this is your first answer. Next up, how much will it absorb? Okay, so remember, absorption was how much energy will it absorb upon how much energy is incident. So absorption coefficient was 0.7, okay, and how much will it absorb upon how much was incident? Incident was 200, therefore the amount of energy absorbed will be 200 into 0.7, which is 7 to the 14, 140 watts. That's the rate at which the energy will be absorbed. Keep this in mind. Oh my god, thank you Princey. Carrots, bananas, my god. Carrots remind me of seashells. Yeah, I went to Seychelles last year, my god, I didn't travel anywhere last year, I just forgot about it. And everywhere they just used to give me carrots and fishes, that's it. There's only two things. And cabbage maybe, and that not the fried cabbage, there's a dry cabbage, that's all. Can radiation from cooler body heat a hotter body? Yes, Sanchit, and that's our next law. For sure you're going to see that. That's going to be our next law. Let's see the next problem, and after that I will show you that problem where a colder body can also heat a hotter body. Yes, you'll see that. All right. So here is the question: if E lambda and A lambda be the emissive power and absorption coefficient respectively of a body, and E lambda be the emissive power, my goodness, I'm going to get confused. Look at this, of a ideal black body, then from Kirchhoff's law, which of the following is true? Let's see, don't get confused. Let's see. If E lambda is emissive power and A lambda is the absorption coefficient. Okay, according to Kirchhoff's law, E is equal to A. Now A is absorption coefficient. So what is the absorption coefficient symbol here? It is A lambda, guys. Now what is E? E is nothing but how much is emitted by a normal body divided by how much is emitted by a black body. So in this case, how much is the emissive power of that normal body, of that body which is there? It is nothing but E lambda. So on the top you will have E lambda. The black body has an emissive power of capital E lambda. So capital E lambda is over here, and this is A lambda. Now just check which one is true. E lambda, E lambda, A lambda. Okay, just check this out, guys. I believe C is correct. Just check this out. Option C is correct. Check this out. Yes. Okay, cool. Yaar, I cannot talk in Hindi because this is a special channel P, because we have created this channel for English medium students. We have Hindi medium channels also separately, and understand we are going to learn in English out here. But yeah, if you want to talk to me in Hindi, for sure you can chat with me on Instagram. All right, let's get going to the next question. And for that we need the next theory. Yes. Hold on, Sanchit, hold on. You will see the thing right now. That is what I'm going to tell you. Prevost theory of heat exchange. Now you would have studied heat flows from hot body to cold body. That's correct. Not a problem in that. But when temperatures of two bodies are equal, that is when thermal equilibrium is achieved, you would have studied heat does not flow. Yes, correct. But in conduction, yes, in conduction, what we studied last time, when two bodies have same temperature, no heat goes from here to here and no heat comes from there to here. But in radiation, there is a special thing that happens. You know what is that? In radiation, even when the temperatures are equal, yes, you heard me right, even when the temperatures are equal, you will see this body will be emitting some radiation. Okay, this body will be emitting some radiation, and this body will also be absorbing some radiation. Yes, just that the two rates will be equal. Whatever is emitted will also be absorbed. So if something is absorbed over here, and that same thing would be emitted from here, and understand this thing will again emit it, and the same thing will be absorbed over here. So if this is happening only via radiation, then understand the amount of emission and absorption is equal in thermal equilibrium. This is something like the dynamic equilibrium you have studied in chemistry. So these two rates are equal. Keep this in mind. So I'll mention this. At thermal equilibrium, very, very important, rate of absorption is equal to rate at which it is emitting radiation. This is only at thermal equilibrium. Keep this in mind, not any other time. Very, very important. But for example, the heat which is absorbed is more than heat which is emitted. For example, what if this happens? If it absorbs more heat and emits less heat, then you will see the temperature, yes, will increase. Think about it. Why? It is absorbing more heat and emitting less heat. I hope this is clear. And similarly, so this is one point which you should know. And similarly, if the heat which is absorbed is less than the heat which is emitted, then obviously the temperature is falling down. I hope this is clear. So that's why I said even a colder body can exchange heat with the hotter body, but the net heat will always come from hot to cold, net. But the cold body can still give heat to the hot body. I hope this makes sense. I hope this is clear. I hope this is clear. Is everybody understanding it? Yes. I hope this is clear. Cool, 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 cool. Let's get going. Now, what is the final law? Let me tell you the final law that is very important, and this is how it works. Remember, heat which is emitted per unit time is E sigma A, temperature of that body raised to 4. Similarly, remember, heat which is absorbed is A sigma A, but temperature, where is it going to absorb from? The surroundings. Temperature of the surroundings raised to 4. So hence, when I do the math, okay, the net heat flow, okay, which will be the net heat flow. It is emitting and it is absorbing. So what is the net heat which is coming inside the body? It will be the net heat which is getting absorbed minus the net heat which is getting emitted. Think about it. Some amount is getting absorbed and some is getting emitted. So the subtraction of these two, and you can guess what is going to happen next. This value of A is actually equal to E because of Kirchhoff's law. Kirchhoff's law, do you see that? Hence, what are you going to see? When you subtract these two, E sigma A is constant. You will have temperature of the surroundings raised to 4 minus temperature of the body raised to 4. This is the final law. This is the net heat flow rate which will be coming inside the body. Keep this in mind. Very, very important. Is that fine? Now you understood it. Why white and black color don't have wavelength? Okay, first of all, Ankit, black is not a color. Black is lack of color. Okay, so that's why it does not have wavelength. Next thing, white is not one single color. It's not a monochromatic light. It's a mixture of colors. So that's why white does not have a specific wavelength. Okay. Sarthak, this is heat transfer, 11th standard topic, and we are doing radiation. We completed conduction last lecture. Okay, cool. Let's get going to the next set of questions, but one last law before we go to the next question. Have you experienced this, especially during winters, that the water initially, when you leave hot water in the bucket, it becomes cooled really fast, okay, initially, but later on, once it becomes lukewarm, it takes a long time for it to come to room temperature. Let's say the water is boiling hot, okay, maybe you have served some coffee or maybe some hot water in a glass. It cools down really fast initially, but later on it takes a lot of time to cool further ahead. Haven't you experienced that? Yes, yes. So now this is what Newton saw, and he gave the Newton's law of cooling. So let's see what this Newton's law of cooling is. And Newton's law of cooling says that the rate of cooling, okay, the rate of cooling is directly proportional to the temperature of that body minus temperature of the surroundings. This is what he said. The rate of cooling is directly proportional to temperature of the body minus the temperature of the surrounding. Basically, rate of cooling is rate of change of temperature is directly proportional to the difference of body's temperature minus the surroundings temperature. Now, because there is a proportionality, you can get rid of it and it will become dt by dt will be minus some constant. Okay, why that minus? Because it is cooling, right? Because of this word cooling, so you can put a minus sign so that the constant is positive, and you will have temperature of the body minus temperature of the surrounding. This is the final law that you should remember. Rate of cooling is minus K, difference of the temperature of the body minus surrounding. Okay, keep this in mind. All right, cool. Let's get going and let's start solving problems. Guys, I hope you guys are making notes. I hope you guys are also having fun while learning, and I hope you are also making friends, and I hope you have already liked the video, and I hope you have already subscribed to the channel in case you have not. All right, do that. Very good, very good, very good. Cool. Let's get going to the question, and here it comes. It was asked in 2013. Which of the following graphs is the correct representation of temperature versus time for a body like a metal piece which is heated and left to cool in a room which is at some temperature theta naught? Come on, which of the following is true? Come on guys, think about it. Yes, very simple, very simple, very simple. Very good. Very few people actually, now that I see. Okay. Ankit, if you have taken subscription for 1 month, guys, I have a beautiful news for all of you. Before I show you the answer, you know what the news is? I am starting Erudov course for all the students of 11th, 12th and dropper students. Erudov. All the 11th standard problems, I'll be discussing, the most important questions from Erudov, of course. I'll be discussing from the Erudov book in this micro course, and it is going to start on 8th of February. So if you are in that pro subscription, that's it. You can get the course for free of cost. Yes, 0 rupees. And that's the advantage of pro subscription. You don't have to pay for all the courses which will be launched. In fact, I had just launched HC Verma course, discussion course few months back. That's over. You can watch all the recordings if you're in the pro subscription. Also, few months back, I had launched the derivation course, derivations of all the chapters of 11th standard that can be also seen as replays, or you can attend live sessions whenever it is happening, again at free of cost. Yes, surely Ankit, I'll definitely tell you. So Sarthak, basically it's IE Erudov, the most famous book, the most difficult book in fact for physics if you want to clear JEE. And yes, you can just ping me on Instagram, I'll tell you all the details. The correct answer is C, guys. Yes, the correct answer is C. So understand guys, Newton's law of cooling said that the rate of cooling depends on the temperature difference. So think about it. If this is the temperature, okay, this is the temperature of the surrounding, okay, then if I draw a tangent to this curve, okay, think about it, that slope of that tangent will be dt by dt, because if this is temperature versus time graph, the slope of the tangent will be rate of change of temperature with time. And what did I just tell you in Newton's laws? This is minus, it's negative, that's why the slope is downwards, K times temperature minus temperature of the surrounding, isn't it? Now, do you see, this is right now over here, in case you are still not able to figure it out, this is right now the temperature difference, T minus T of the surrounding. Now, as the temperature falls, won't this value reduce? As temperature decreases, the delta will also decrease. That means the slope magnitude will also decrease. this value will also come down. If this value comes down, this should not be so steep. It should be less steep. That's why the graph goes beautifully like this. That's why initially if it takes some time to cool, it takes longer time for it to cool by the same amount. You can see that in this graph. That's the beauty of this graph. I hope this is clear. Yes. I hope this is clear. Yes. Cool. Let's get going. Last question for today. 2014 question. Hot water cools from 60 to 50 in the first 10 minutes. And in the next 10 minutes, it goes to 42. What is the temperature of the surrounding? These were the options given. Let's not worry about the options. Let's just solve the question as it is. And if you feel you can solve it on your own, please go ahead. Simultaneously, all those other students who want guidance can look at how I'm solving this question. Okay, let's try and do this. First, let's assume, okay, the temperature of the surrounding to be T. This is the temperature of the surroundings. Okay, cool. Now, what is the temperature of the body initially? It is 60 degrees Celsius. Okay, then it goes to 50 degrees Celsius. Then it comes down to 42 degrees Celsius. From here to here, it takes 10 minutes. And from here to here, also it takes 10 minutes. Great. Now, think about it. What is the rate of cooling initially? So, for this part, okay, for this part, the rate of cooling, because let's use our Newton's law. What does Newton's law say? Rate of cooling, okay, rate of cooling is equal to, okay, some constant, doesn't matter, negative constant, positive constant, into temperature difference, all right, temperature of the body minus temperature of the surrounding. That's what we got to know. So what is the change in temperature from 60 to 50? So 60 minus 50 upon 10 minutes is equal to some constant, okay, some constant into temperature difference. Now what is the body's temperature difference? Is it 60 minus T? Is it 50 minus T? Because at every instant the temperature difference is changing. So why not take the average? Yes, take the average. What is the average of these two guys? What is the average? Isn't it 55 degrees Celsius? This is the average value of the temperature. So note down what is the temperature difference, average temperature difference. So won't it be 55 minus T? I hope this is clear. So this will be 1 is equal to some constant into 55 minus T. That's the first equation. I hope this is clear. Now, no need of infinite GP. Next up, from here to here, think about it. What was the average temperature from 50 to 42? Think about it. Isn't it 46? That's the midpoint. That's the average temperature, guys. So now, again, look at what is the temperature difference between this and this from here to here. It is nothing but 46 minus T into that same constant. Instead of 50 minus T or 42 minus T, don't get confused. Take the average, which is 46. 46 minus T is the temperature difference of the body and surrounding, is equal to rate at which it has cooled. From 50 to 42, how much is the change? 8 degrees. In how much time? 10 minutes. So it is basically 8 by 10. Therefore, you will get this as 4 by 5, all right, is equal to some constant, or you can take it to the other side if you want. So 46 minus T. This is what you're going to get. Now that we have both the equations, just solve them, guys. I won't need this anymore. Let's get rid of this. I don't need this. So just divide both of them because that constant will go away. So you will have 4 by 5 divided by 1 is equal to, okay, 46 minus T divided by 55 minus T. Remember that constant has gone when I divided it. So that constant has gone. So this will become 55 minus T, okay, into 4 by 5 is equal to 46 minus T. Now 55 by 5, 11, 11 4 is 44. So 44 minus 4t by 5 is equal to 46 minus t. Shift it a little bit here and there. So t minus 4t by 5, brought the t over here, shift 44 over there. So it will become 46 minus 44, which is 2. And that's it. T minus 4t by 5 is t by 5. So t by 5 is equal to 2. Therefore, t is equal to 10 degrees Celsius. So I've just solved it very neatly for all of you. That's how you get it. I hope this is clear. Yes, this is what happens. So Hemant, I'll tell you what needs to be done. See, the logic is initially from 60 to 50, the temperature change was 10. 10 degrees changed in 10 minutes. So that's the rate of cooling. That will be some constant into the body's temperature difference with the surrounding. What is the body's temperature? Should I take it 60 or 50? No, take the average. So 55 minus T. So make one equation. Next up, for 50 to 42, okay, for 50 to 42, what is the temperature change? 8. In how much time? 10 minutes. Do you see that? So it has changed by 8 degrees Celsius in 10 minutes. And what's the average temperature? 50 and 42's average is 46. So average temperature minus surrounding temperature. Do this, you will get the second equation. Now divide it, that's mathematics, and you will get the answer. I hope it is clear now. Yes. Yes. Okay, cool. Let's get going then. So I have kept some questions. Yes, 10 degrees Celsius, that's the answer. I've kept some questions for you guys to solve at home. The answers are also put in the, I'll be putting it in the Telegram group. So please join the Telegram group and you can check out these homework questions in the session PDF. In case the session PDF is not uploaded, please let me know. Don't worry, you'll get the session PDF. But worst case, why don't you take a screenshot of this? You can just take a screenshot. Jaideep, you can take the average in Celsius. Keeping everything in Celsius will also work. Okay, so yes, cool. So this is the first question. This is the second question. You can take the screenshot. All right. Just take the second question, screenshot. All right. And the answers, everything will be posted in the Telegram group. So remember, the crash course for all those students who want to clear the JEE examination, the upcoming JEE examination, the second attempt, third attempt, doesn't matter. The crash course has already started where you are going to get the most dedicated team. So I know the teachers personally, they are really good and they have been training kids for a long time. And also you can check out our results last year, what we did. There are 500 students at least who cleared JEE Advanced. I'm not saying JEE Mains. JEE Mains was in thousands. JEE Advanced, there were 500 students who cleared it. So you should go with the institute which has a proven track record and obviously which has all the syllabus planned out for you, the entire 11th and 12th syllabus with obviously the doubts clearing facility. So because if doubts are not cleared, if it is just one way teaching, then it's of no use. So that's also very important. Go check out all the details. From morning till night, there will be teachers available for all of you for getting your doubts cleared. And the most important thing, how can I forget, guys? Test series. 20 tests, mock tests with discussions. Yes, live discussions which will be happening in these crash courses. So go check it out because the crash course will be available at a very discounted rate, nominal rate. This is just to make sure, the livelihoods of all the teachers and all the people who are solving your doubts, plus whatever servers and the internet that we need to maintain is covered up. That's the nominal price that we are charging. So discount of 20%, like you can see, from 10,000 to 8,000 when you use the coupon code SHCC. So use this coupon code and change your life, guys. All right. So somebody was asking, yes, Ankit, what are you asking? What doubt you have? Yes. I'll reply to your comments. Yes, sure. Yes, I'll definitely tell, Ankit. I think you have posted your comments in the previous video. Definitely, I'll tell you. Don't worry. Bye guys, all the new timers. I hope you have subscribed. If you have not done it yet, please click that button. And if you have already subscribed and if you want to support us, if you want to show your love, do hit that like button out there. Bye bye. This was Shreyas here, your master teacher. Tomorrow we'll meet at 7 o'clock again sharp for discussing AC circuits and LCR. Bye bye.